Hello, today I want to implement a cloth solver using Vex inside of Houdini from scratch. Why this, you may ask? Well, lately, position-based dynamic effects are quite popular. We have grains, which is PBD, and then we have the next step in PBD tech, which is XPBD-based Vellum. And people love these solvers because they are fast, they deliver good results, and they are stable. So today I want to implement the ancestor of all of these techniques. As doing so will give us quite some insight in how PBD systems work and why they work the way they do. There is an article on Gamasutra called Advanced Character Physics. It's by Thomas Jacobson and it was published in 2003, and it deals with the physics used in the game Hitman back then. This article describes sort of the predecessor of all PBD tech. It is using a Verlet-based integration scheme, and it is using constraints that are projected to solve them in an iterative fashion, using Gauss-Seidel iteration. We want to do this concurrently, so we will use Jacobi iteration, but nevertheless we will implement this article. So go through the article if you're interested, but I will explain everything so you don't have to read it if you don't want to. Before we start inside of Houdini, let's first get some theory out of the way. Okay, how do we model a piece of cloth? Well, we use particles. We define a particle for every vertex of the cloth, and then we simulate these particles using the laws of physics. Later, we want to constrain these particles by constraint lines, like so, to tell them to stay a certain distance apart, because cloth is not totally stretchy, but it is defined by the fact that it is not stretching out too much. So the first step is to simulate the particles, and this is usually done using Euler integration. Euler integration. First, remember the first law of motion by Newton, which is the force is the mass times the acceleration. In our case, we want to assume that the mass is 1. Let's say m is 1. Then this formula simplifies to the force is the acceleration. So to make particles move, we want to integrate the force to velocity and then the velocity to position. And this is usually done by the formula v prime. This is the vector quantity, the new velocity, is the old velocity plus the acceleration times delta t, being the time step. And then the new position, x prime, is the old position plus the newly created velocity times delta t. So this is a double integration, and it will give us the new position of the particle in the next frame from the forces acting on it in this frame. This is a standard method, but it has a flaw for our purposes, and this flaw is that it uses the velocity vector. Because later, to implement the constraints, we want to use projection, so we want to just move the particles to the right spot to fulfill the constraint. And if we do this with Euler integration, the velocity gets out of sync. So we have to update the velocity all the time, and that is very cumbersome. So maybe there is a better integration scheme that can be used that has the velocity given implicitly, and there is. In the article on Gamasutra, they are using Verlet integration. The difference being that Verlet integration has the velocity given implicitly. So instead of using the velocity vector, Verlet integration is storing the position of the particle from the previous frame and then is approximating the velocity from this information. So Verlet integration looks like this. X prime is 2x minus x star, and this is the previous position of the particle, plus acceleration times delta t squared. And then, of course, we have to update the previous position. So the new x star will be the x from this simulation step. This is Verlet integration. And you see, we have no velocity here. but we have a previous position, and that means as soon as I move a particle, the velocity will be calculated correctly automatically without any further work on our side. But how can we derive this formula from this formula? Well, that's not too complicated. The first thing is that we can plug this very first velocity step here into the position update. So let's write x prime is x plus v prime, and v prime is this expression here. So v plus a times delta t, like so, and then everything times delta t. So now we just replace this v prime here by this expression. Now let's get rid of the parentheses. So x prime is x plus v times delta t plus a times delta t squared. I just multiplied both terms by delta t. Great. So how can we get rid of v times delta t? This expression is containing the velocity vector. Well, let's think about the previous frame for a second. So this is the formula for x prime. But what about the formula for x? So x is the previous position, x star, plus the previous velocity v, instead of v prime, times delta t. And I am interested in v times delta t. So by rearranging this, I can write v times delta t is x minus x star. Now we have a pretty nice expression for v times delta t, and we can plug it into this formula here. So let's continue with x prime is x, and now let's replace this term here, plus x minus x star, this term is now replaced, plus a times delta t squared. And now, if we get rid of the parentheses again, x prime is 2x minus x star plus a times delta t squared. And that is our formula for the Verlet integration. Great, so let's go into Houdini and implement this Verlet integration step to solve some particles. Okay, let's create a geonode. Lay it down, dive inside. Inside, let's create a grid. Make it 1 by 1 and give it 20 by 20 subdivisions, like so. This will be the grid we want to simulate. One thing we want to do now, but we will use it later, is to append a divide sub. And this will just split all the polys to trees, giving us a diagonal connection. This will be important for the constraint later. Now, before we implement the solver, let's configure our system with a wrangle. So lay down a point wrangle, append it here, and call it configure. And this is just used to set old x. So let's create a new attribute of type vector called old x, that is a previous position. And I want to initialize it to the current position, because in the very first frame there is no old x. Now that we have that, let's append a solver, a subsolver. Make it visible. Before you dive inside, please make sure to lock this view, because still in Houdini 17 the subsolver has some issues with updating, and if you lock this view here, so this network, you always get the correct results in the viewport. Now that you've locked the view, dive inside. The very first thing we want to do is to deal with a flaw of the previous frame node, because in the very first frame there is no previous frame. So in the very first frame we want to read the inputs of this input 1 node. So lay down a switch, connect the previous frame and the input 1 to the switch, and write a little expression reading $f double equals 1. And that means in the very first frame the solver is reading the information from the first input, and after that it's reading the information from the previous frame. Now, before we implement the Verlet integration, let's first create forces. So lay down another wrangle, and let's call it forces. And let's create a gravity force. So let's create a new attribute. I mean, Houdini has this force attribute that is used in all the dynamic contexts, but I want to use something different, not to mix the things up. So let's create an attribute called vector Verlet force, for example. With the T here, Verlet force, and this should be gravity. So 0 minus 9.81, 0, like so. This is gravity acting on our particles. And I have a little typo here. This should read as a point, of course. Now we have forces on our particles. Time to implement the Verlet integration. So lay down another point wrinkle. And let's call this one Verlet integration. And implement the formula that we derived a second ago. But before we update the position, first let's create a new vector called temp to store the current position, because we will need it later to update the old position. Then let's read the old position. Vector old x is the attribute v old x. I mean, you can use this attribute here directly, but I think it's a little clearer to copy this into a local variable first. I prefer working like this. So vector force, same thing here, will be the attribute v Verlet force. And now let's update our position. So add p. And now plus equals. So we want to add to the current position. And remember, in the formula we had 2x, but now we only need 1x because we wrote plus equals. So add p minus old x. So this is the old position, this is the current position, this is the new position, and we are writing plus equals, and that means we don't have to use 2 at p here. Now we want to add the acceleration, which is the force. And now we want to multiply by delta t squared. And inside of Houdini we have this global variable called time inc. And of course I can put this to a power, but an easier way is to just multiply it 2 times. So time inc times time inc. So now we have exactly the formula we derived. And now let's update v at old x with the temp value that we stored. Press apply. We have an error here because I forgot the equal sign, like so. And accept. And now let's press play. And you see, it is working. The particles are falling down due to gravity. So we implemented our particle system. To create cloth from this piece of falling particles, we want to implement constraints. So now for the constraints, go up one level, and for the constraints we want to use primitives, because that is a straightforward way to define constraints. We want to create lines that connect two particles that are constrained. And in Houdini we have this great convert line, SOP, here it is. If you attach this, it will convert all the polygons to individual lines. So now if you turn on primitive numbers, you see that you have one single line for every edge from the original geometry. And not only that, but at the same time it computes a new attribute called rest length and stores the length of the edge into this rest length attribute. And we will need this rest length for the constraint iteration step. But before we implement the constraint iteration step, well, we have to do this in front of the solver here, and then we want to feed the results here to the second port of the solver, like so. But before we implement the constraints, let's switch to Photoshop and quickly think about how to implement them. Let's think about what we want to achieve. Well, we have a piece of cloth. Let's draw a portion of it with just 4 polygons. Here we have the particles, and these particles are constrained by the lines between them. And these lines have a rest length. That means they are telling the particles which distance to stay apart from each other. Now the forces are pulling on the particles, and that will distort our grid. So maybe we get a state like this, where all these constraints are stretched and the lengths are not correct anymore, like so. So what to do now? Well, we should solve all these constraints at the same time, because if I move a particle, it not only affects this constraint's distance, but this constraint's distance too. But that is very complicated. For this, we would need a linear system solver. Another idea might be to just go through all the constraints and just satisfy them by projecting the particles one at a time. So what if you have a constraint and say this is a rest length, like so. So if you are in a situation like this, where the distance between the particles is too large, just move the particles to the correct spot. And if you have a situation like this, where the distance is too short, move the particles outwards, like this, to satisfy the constraint. But then, of course, if you do that for the very first constraint, you will move these particles, and the other constraints connecting to this particle will get invalid. Nevertheless, the good thing is, if you iterate this process, so if you do this one constraint at a time, and then project the constraint such that the distance is correct, do this for the next one, rendering the first one invalid, sort of, then going through the entire array of constraints, and then just starting over, the errors will get smaller and smaller and smaller over time, and finally the whole thing will converge to the right result. So all the distances will converge to the rest length. And that is called Gauss-Seidel iteration. So if you do this one constraint at a time. The problem with this is that it cannot be computed in parallel. So what we want to do instead is another technique called Jacobi iteration. It's very similar, but what we do is we consider all the constraints that are connected to a point at the same time. So instead of running over all the constraints, we are running over all the points, and then we calculate these translations not only for this constraint but for this constraint too, so for all the constraints that are originating from this point, and then we are just averaging their effect and moving the particle accordingly. So if you have a particle here and it has two constraints, but in reality it should be here and here, like so, then we are calculating this offset here and this offset here. Let's call this A and this B, both of them being a vector. Then we add them together, divide them by 2 because it's 2 constraints, and move the particle accordingly. And then we go to the next point. And then we iterate this process over and over again, let's say 20 times, and it will converge to the correct result without the need for a linear system. Perfect. Let's implement this. Dive inside of the solver and add another wrangle, point wrangle, because we want to run over all the particles and call this satisfy constraints. Great. But this wrangle not only needs the information of the particle, but at the same time the information from the constraints, and these are coming in over input 2. So connect input 2 to the second input of this wrangle and make the wrangle visible. Let's press Alt-E over this text field here to open the Vex editor. So the very first thing we want to do is we want to read the constraints. So let's create an array of type integer called myConstraints, like so, and let's read all the primitives that are connected to the currently processed point. There is a Vex function for this called pointprims. Then you have to specify the geometry stream, which is 1 in this case, because the constraints are coming in over port 1. And then you have to tell the function the point number, ptnum, the number of the currently processed point. Now it stores all the primitives in an array. Now let's create a vector called displacement. And let's initialize it with 0. We want to calculate it later, and then we need a weight. The weight is just the number to divide all this displacement by and initialize it to 0, 2. Now let's run over all the constraints we found. So let's create a for each loop. An integer called constraint. This will be set to the currently processed constraint in the loop, and then we have to pass the array of all the constraints. My constraints, like so. Then parentheses, open and close. Great. Now we are running over all these primitives, but we want to calculate offsets of the points, so we first need the points. Let's read the points from the primitive. Let's create another array of type integer called constraint points PNTS. Again, this is an array, and the function to read the point from a primitive is called prim points. Makes sense, as point prims gives the primitive from a point, and prim points give the point from a primitive. Again, the geometry is 1, and then we pass the constraint, because this is a currently processed primitive. After that, we have the 2 points of our currently processed constraint in constraint points. Now let's read the positions. Vector pos A is the first point of this constraint. And let's use a point function to read the position, point, 0, and we can use 0 here because the points are the same in geometry stream 0 and 1. The attribute to read is P for position, and then constraint PNTS, and we want to read index 0, like so. Now let's copy this line and paste it directly beneath it, and this will be position B. And for position B, we want to read the other point of the line, that is index 1. Now we have the 2 points. Now we want to calculate the vector between the points. So another vector called delta, because delta specifies a change between pos A minus pos B. So this will be the vector between the 2 points. Now let's calculate the length of this vector. So float, let's call it delta length, and this will be the length of delta, like so. And now we need the rest length of the constraint to compare this delta length to the rest length. So another float, rest length, and the rest length, I mistyped rest length, like so. And the rest length is a primitive attribute, so we need the prim function. A primitive attribute of the primitive coming in over port 1. The attribute is called rest length, and the ID is constraint, because that is a currently processed primitive. Now that we have these 2 length values, we now can calculate the error, so the difference between both of them. So let's create another float called error, and let's just calculate the difference between rest length and delta length, like so. And now let's divide it by 2 or multiply it by 0.5, that's the same thing, because this error should be used on both sides of the constraint to move the particles. So the first particle should be moved by 0.5 and the second particle should be moved by half of this error. So that's why I directly multiply by 0.5 here. Okay, and now we can say displacement plus equals, and now we normalize our vector to get the direction. So we normalize delta, which is a vector between the 2 points, which is the direction of the constraint, times error, which is the amount we want to move, like so. And now we have to increment the weight by 1. So weight plus equals 1.0, like so. Now this loop is running, and for all the constraints it's calculating a displacement, adding all the displacements up in the variable displacement, and incrementing weight for all the constraints. So after the loop has finished, we have a weight value, that is the number of constraints, and we can use it to divide the displacement by this weight. But there's one thing that we missed, and that is the direction. Because we want to move the particles in the correct direction. And it's not necessarily true that the primPoints function always returns the current point first. So we have to check if the direction is correct. And if not, we have to invert it. So let's create a new float called direction, or dir, initialize it with 0. And now let's create an if statement. If constraint points 0, so the first point returned from the constraint, has the same ID as the currently processed point. If this is the case, then please set dir to be 1, because then the direction is correct. And else, if this is not the case, so if the other point is the first point, and this depends on the order of the primitive, then please set dir to be -1, like so. Don't forget the semicolon. And last but not least, we want to multiply this dir here at the end of this line to create a displacement in the correct direction. Okay, now we are done. Last thing that we missed, or that we did not implement yet, is to update the position. So add p plus equals the displacement for all the constraints divided by weight, like so. Let's apply, see if we have errors. Doesn't look too bad. And let's accept. If we press play, not much should happen. Yeah, everything falls because we have nothing to hold the particles or to keep the particles from falling. So let's quickly add another wrangle, point wrangle, and call this pin to pin 1 point. And let's implement this one. Let's say if ptnum is 0, so if this is the very first point in the geometry, then at p, the position of this point should be, say, 0, 1, 0, like so. And you see, that has the effect of moving the very first point to this location here and fixing it there. And if we now press play, you see everything is falling down. But if you have a close look on this stuff, you see that the constraints are sort of working. The problem is with this, and that's why everything is falling down, that we are not iterating this constraint loop. So we are just satisfying the constraints once, and that is problematic because it invalidates a lot of the constraints. And that is not enough to hold the cloth to the pinpoint. So what can we do to change the situation? Well, we can run this satisfy constraints inside of a loop. So let's just lay down a for loop. For loop with feedback, like so. And let's move these 2 nodes here into the for loop, like so. Don't forget to reconnect the constraints, to satisfy constraints. And now let's give it 20 iterations. Make this last node visible, and let's see what happens now. And you see, now it is working. Now the constraint solver really solves the constraints, and because it has 20 iterations, it manages to finally converge to the right result. First, the gravity is pulling on the particles. That means that these constraints here that are connecting to the pinpoint get stretched very, very much. But over time, the thing is converging to the right solution. And if you need more stiffness, what you can do is just to increase the number of iterations on this for loop. So what happens if we increase the iterations to 100? Then you immediately see that the result in the very first frame is different already. And you see now it's of course slower because it's going over 100 iterations, but it's a lot stiffer because the constraints are solved a lot more rigid now. And maybe let's make this pin a little more interesting by saying else if the point number is, let's see which point to constrain. Let's go up one level. Well, of course, now it is erroring out because I wrote this here. Let's take it out quickly just to see the point numbers. This is 380. So let's constrain point 380. So else if point number is 380, what should happen then? Let's say position should be position should be 0, 1, 1. But not only if the point is 380, but at the same time, so and the frame, add frame, is bigger than 40, like so, just to make something interesting happen. So let's see what this gives. Solving, and now with frame 40, it is moving over there, because now it's pinned to this location. And you see that our cloth solver is working. So it is giving us a cloth-like effect. Let me click this little stopwatch to make it real-time playback, and you see that we have implemented a cloth solver from scratch. And by going over the code, I think you understand why the constraint iterations in the grains nodes are so important for the stiffness if you're using cloth with grains. And the basic principle really holds not only for grains, but for vellum too. That said, I have to point out that a big advantage of vellum, being XPBD, is that they managed to get rid of this dependency on the constraint iterations. So the constraint iterations are only controlling the quality with vellum, not the stiffness anymore. But with grains, which is just PBD, it is exactly the same as here. If you have a low number of iterations, it will be very springy. And if you have a high number of constraint iterations, it will be a lot more stiff. And that concludes building a cloth solver from scratch inside of Houdini with Vex. So now you know the basics of position-based dynamics, the very basics. If you want to do more complicated effects with position-based dynamics, if you want to use XPBD, and if you are interested in the vellum solver, consider going over to Patreon, because at the moment we have a new course on Patreon dealing with XPBD, so with the vellum solver, and explaining all the ins and outs of using the vellum solver. So check it out on Patreon. A very big thank you goes to all our patrons, especially important-looking pirates, Kyoko Sakane, PU Online Learning, Chris Hebert, David Adan, Derek A. Johnson, John Kunz, Joseph Howerton, Mohammed Al-Abri, Nick, Rafik Anadol, Rob Bryan Jr., and Roger Lloydholt. Thank you so much for supporting us and making all these tutorials possible.